Okay, so the only one that I really was concerned about when I looked at y'all's papers is C. So do note that the only time you can have zero is for, zero for free elements is for which cases? Delta H and delta G, but not delta, or sorry, not delta, not S, not entropy, absolute entropy. So the reason they don't give it to you up here is because they want you to know when you're finding G here, you have to use zero for the diatomic hydrogen. So how did you guys calculate S in terms of, and basically for B, how did you guys find delta S? Okay, so I heard delta S meaning products minus reactants, which you cannot do in this case because note it, you cannot assume zero for that H, so you cannot do S products minus S reactants. You actually have to do delta G is equal to delta H minus T delta S. So on A, just take products minus reactants for delta G values because everything is given to you except for the zero, which you write the zero because you're cool. You know that there's two hydrogens, so make sure you're writing your zero there because you get points there. That should give you negative 28.9 kilojoules. And then this is my note to myself. I want to do S products minus S reactants, but I can't because I don't have the value for the H itself. So you need to go about it another way. You have to find delta H first to plug into G is equal to delta H minus T delta S. So I went ahead and found that first utilizing the data in the table. Now again, I just assumed what? Zero for this two times the H diatomic gas. So it's still products minus reactants. You get a negative 128.1 kilojoules per mole. Presents? Yay! And then after you plug in the delta, big graduate cylinders? Last. I don't know what this is. Okay, so after you plug this into your delta G is equal to delta H minus T delta S, you're solving for what? Solving for delta what? Delta S, and then you're going to get a negative 333 joules per mole K. And that's fine to be negative because what are we speaking to here? Like, what is this representing? Entropy change over the course of a reaction, which in this case, it's increasing, or is it decreasing in entropy? Decreasing entropy. So that's when you know that you're fine for some of the change. But then after that, you had to find delta H, delta G, and S for the free element H2. So you had to go about it a different way because you already knew the zeros for the H and G. So that's kind of what I stated up there. So since you then had the delta S and you had pieces of products and reactants, you had to solve for 2x, right? So note there were two hydrogens here. That was a mistake, a common mistakes people make. So when you're solving for this here, negative 333, which you got previously, isolating the x, divide by negative 2, you should get positive 131 joules per mole K. Cool? All right, I did not go over point values. I can do that later if you guys want to. Last piece here is 5. I think most of you guys actually did well with the first part of 5. A lot of people asked me about C. What other struggles do we have here? Yeah.
Just a general question. So if we accidentally put negative instead of positive, positive and negative,
so I follow the AP College Board rubrics as best I can, and if it's the points for the final answer, and it's usually correct sign and correct units. If you don't have correct sign or correct units, you can get the final point, but you probably got process points. Okay. So we'll have to be very careful. I even put on the top of the FRQs for tomorrow's test. Be aware of surrounding systems, positives and negatives. Okay, like just be very cognizant of that. All right, so you have data for A. How did you guys solve for A? What equation? Come on. S products minus S reactants, right? So you had the S total change, solve for the one product that you didn't have information for, given the two reactant values given. So you should have gotten, I keep putting delta, it's a bad habit of mine, but S of ethane is 229.6 joules per K, or joules per mole K. And then for B, calculate the G for the reaction. What does the G mean about, the sign mean about the reaction? Given you have everything to plug into delta G is equal to delta H minus T delta S, you first had to find your own delta H, and that would be for the total reaction exothermic, negative 311.4 kilojoules. getting a good approximation there? Yes, yes, yes. And then after that, plug it into your G equation. 298, how do I know it's 298, by the way? Standard conditions is the not, right? And then note the difference in units, so kilojoules, and this was in joules, so we need to convert to kilojoules or vice versa. I would generally convert to kilojoules because delta G is expressed in kilojoules most times, so that's a negative 242 kilojoules per mole. What does that mean about the reaction? Negative delta G. So other than spontaneous, we would say thermodynamically favorable. I'm allowing you guys to use those, but try to make sure you're sticking more to the thermodynamically favorable. And if you get tired of writing thermodynamically favorable, just like abbreviate it at the top and just say this means TDF, and you use TDF the rest of the time if you have to explain anything. Lastly, you had the delta H you just solved for up here. Use that as your delta H reaction. Plug in the pieces that you know in terms of bonds broken minus bonds formed, which is technically reactants minus products, the only one we flip. Solve for your triple bond, which is in the bonds broken, so the reactants. And as you plug in that X right there, input all your data, solve, you should get approximately 819 kilojoules per mole, which, does that make sense for a triple bond? Yeah, it's pretty large. And you can compare that to your single bond you have here, which was, what, 347? So it should be almost 3 times as big. I mean, it's not 3 times 100%, but it's a much larger number. Does that make sense? Okay. All right. So can we check a couple of those thermodynamic filters, like the first 10? Can I do that? I do want to give you the answers before you go. So I mean, we got like 18 minutes left in class. You do the first 10, and then I'll pause and you guys can chat with each other. Actually, I want you guys to answer the first 10. Ready? One. All right, so here's our, I need cool letters. Apple, banana, Charlie, dog, elephant. Ready? Elephant, okay. 2. Dog. Okay, so some of these definitions are kind of, they're rogue right now. They're going to be really more important to us later on, but they are involved in thermodynamics. But don't keep yourself over these definitions. The ones that you should know are the ones we've dealt with most often, like free energy, kinetic energy, so forth. Okay, so 2 is dog. 3, apple. Good. That's a random definition you'll need to know in like April. Okay, so if you don't feel that on mine. 4, banana. Thank you. 5,
Elephant.
so confident. Dog. It is dog. Energy given off when a substance condenses, which means state change of wet to wet. Gas to liquid, which is the same energy it takes to go from liquid to gas, which is the opposite. So it says heat of vaporization. It could say heat of condensation, but the numbers are the same. It's just their signs are different. 6, elephant. Good. 7, apple. Good. 8, questionable dog. I heard. Can you give me some more? Anything else? We said apple and dog. Okay. The one term that you should really closely pay attention to here is that the well-insulated, assumed insulation prevents any energy exchange with the surroundings. So what has to stay constant? Total energy, right? So total energy has to be constant. So that kind of, okay, that whittles you down to 3 answers. And then if something is melting, what's happening to it? Technically, it's becoming more disordered, so the system is technically becoming more disordered. So it should be dog. Okay, it should be dog. Now I would go back to banana if we thought about it, but it's kind of it's more dog than banana. Okay. 9. All right, so you're looking for the greatest increase in entropy. So what's happening in dog? All right, so 2 moles of gas went to 4 moles of gas. The total change was 2 moles of gas, right? What's happening in elephant? Solid to gas. So it's like, boom, right? Crazy entropy change. And we're making 3 moles of gas, but only 2, so that trumps it regardless. So 9 is elephant. 10? Apple, because everything else is doing what? Decreasing entropy, okay? I'm just going to keep, can I keep going? Where are we at? Where are we at in this? We jumped around. No, I'm asking where you are, not where I am. You get to 13. Who finished? All right, take you have 5. Do your come on. Pick up where we are, please. Pick where we are. These are good multiple choice questions. Wink, wink. These are really good. I'm not saying these are like on the test. I'm just saying the way they're phrased and some of the concepts. They're not exactly the ones on the test. I'm not that cheap. They're taking on. Sorry, I'll make copies. Product. So tell me your work.
2 times 436 plus 499.
So hold on. So this is 18, right? Okay. So tell me how you do your structures. H bond to H. Okay. How many of these do you have? 2, and then O double bond O. There's only one of those, and we produce 2 H2O molecules, right? Okay. So what number goes with this? This is 2H. So 2 times what? 436. And then this is 1 double bond O. 499. Subtract. So this is the summation, right? And then we're going to subtract what? Okay, make sure we weren't saying 2. That's the piece where people mess up. There's 2 OH bonds, but there's total 2 molecules. There's 4 times what? 464. All right, what's this value? You just show your work for your stuff, right? 872. And then this is 17. What is it? 864. Okay, so then what's our final? Negative 400 and what? What is this? What is this number? I believe Taz most of the time.
No, that's like that's from.
This is this right? And this right? There are 25 of you. Okay. Oh, okay. Sorry. Yeah. Tell me this answer. Tell me this total sum.
1371.
Okay, and then tell me the final.
It's 1836.
Negative 485.
Yeah, that's what I got. C. All right. Yeah, I mean those numbers are close, so you just have to know Butterfingers. What was this? 80, 61, 56. Okay. Negative 485. So it should be C. Watch your fingers. 19. 19? Huh? How do you, okay, I heard apple. Quick, tell me you got apple.
Reaction for the took the delta H for the reaction, and then had this since the heat of vaporization is going from
Heat of vaporization is going from
gas to liquid.
gas to liquid. Okay. Okay. So we're solving. We're basically this is Hess's law, right? So we're solving for what down here? What's our target equation? You're making CO gas, 2H2 gas yields what? Liquid, right? So we're trying to form a liquid versus the gas, right? So what's this equation right here that I'm utilizing? Gas to liquid, right? So we're using the vaporization from liquid to gas or condensation from gas to liquid in collaboration with this to finalize this equation. So we're solving to make that liquid instead of the gas. So this value up here was what? Negative 91 kilojoules. This is what? So vaporization from liquid to gas is positive 37. So what's it in the way that we've written it here? Negative 37. So the answer should be the summation of negative 91 plus a negative 37. So the answer should be negative 128, which is alpha. Good. I mean, alpha. Okay, 20. 20? Dog. Okay, 20 is dog. 21? We leave in like a minute. Elephant. 21 is elephant. 22. Alpha. 23. Banana. 24. Banana. 25. Where'd you get? Alpha? Elephant? Alright, so the first time I had elephant, and the second time I just did it really randomly. I got beta. Nope, okay, I'll put the answer to you later. Bye. I'll scan this. I'll scan it. With some work. I'm not going to go back and do all.